Hey there, everybody. How are we doing this fine Sunday afternoon slash evening slash early afternoon, depending where you are in the world? Maybe nighttime if you're in Europe. How are we doing? What's going on, everybody? I'm just doing a quick audio check, making sure everything's good. Good to hear Laureen and Emily and Benjamin and Cynthia and everybody else. So a couple good things going on in the chat about test dates. If you do have any questions, don't hesitate. Please hit us up. We can talk about it quite a bit, but yeah, we really did kind of want to know. Actually, we're in show. Well, one thing we did want to talk about is where you guys are at in your course. And so one thing to definitely talk about is Molly just took her first practice test this morning. Do we have any brand new people? Like this is your first class, pretty fresh, as we like to say. Cynthia, welcome. All right, so a couple things that I do want to let everyone know about how this stuff works. These classes are meant to be going above and beyond what we cover in your actual classroom course. So this might move a little bit quickly for you if you haven't had any classes yet, because this is actually intended to be taken after you've already had the basics of Therm in your Chem Phys 1 class where we go through a bunch of this stuff. So don't feel like you have to leave or you need to, like have that stuff done first. But I want to warn you guys, it might move pretty quick. It might move a little bit faster than you anticipate. And so if that is the case, please be comfortable to say, all right, this is too quick. You can always come back, watch it again on the archives. You can also, watch, of course, the lessons on demand that are pre-recorded, all that kind of stuff. I just want to make sure you guys are aware of how this works. For those of you that are brand new to the online format, such as Crystal, the functionality we have is in the lower bottom. You got a Q&A. Of course, we got the public chat. We'll be talking quite a bit today. But notice, of course, we got loads of teachers. Liz, Sergey, and Kyle are all here. So if you have any questions, throw them in the bottom, and we can run through anything that you want to talk about. So it should be pretty fun. So at the very beginning, in our very first Therm class here, we're going to talk about energy and thermodynamic processes, different types of transfer, convection, conduction. We'll talk about phase change and all that kind of stuff. And then the later part of it, we'll get really into some passages, a lot of questions, and applications of these concepts. So let's get the party started, and let me know if you have any questions at all throughout the whole course. This will be interactive. It's not meant to be a lecture. Let's talk, let's chat, let's have some fun. All right, so the main learning goals we have today is we're going to talk about the nature and mechanisms of energy. I gave you a couple, such as convection, conduction, and all that stuff. We'll go through the specifics. And we'll also talk about different types of thermodynamic processes. So now, whenever we talk about thermodynamic processes, they're generally types of expansion or compression processes that, can you guys think of any examples, like a type of compression that would be a specific type of thermodynamic process? There's lots of things you could say. Pistons are a great example. They actually go through lots of different types of processes. They do 4, technically. And we'll go through those in our second class today, Molly. But yeah, isothermal, you could talk about isobaric, you could talk about adiabatic, you could talk about isochoric. That wouldn't work for expansion. But exactly all those types of words. And so we'll really kind of go into those. And our last final quiz for today, we're going to go through a slide where you have to identify whether we have positive or negative various terms for a bunch of different types of processes. It should be pretty fun. All right, so let's start off with the fundamentals, and we'll talk about just some nature and mechanisms of energy transfer between systems. So if we're going to do that, we have to talk about 2 main classes of functions. We've got state functions, and we have flow functions. And so notice here, well, actually, let's get our background. So that right there, what's that referring to? Gibbs, exactly. That's our big capital G, so it's the free energy. Exactly. Notice it's in kilojoules, so of course it's times 10 to the third, but mostly it's Gibbs free energy. And if we ever see Gibbs free energy on the MCAT, what's the number one thing that you need to be thinking about, or what they're going to really be asking you about if they're talking about Gibbs? There's one thing more than anything else whenever you see Gibbs. Perfect spontaneity, right? So whether it's spontaneous, non-spontaneous, Hannah's got the equation right there. G, of course, equals, it's chemistry's greatest hits is the formula for that. We'll go through that question today. Exactly. So what would exergonic mean, as Crystal's bringing up? So if you had an exergonic, that's referring to your Gibbs, that would mean that it's spontaneous, right? So then what happens to your free energy? Does it go up or does it go down? Benjamin's getting it right there. It goes down, exactly. So this would be an example of an exergonic process right here. Notice that we're going from our substrates to our products. Now, there are a couple terms we need to know. So for example, what do you call this right here? From the substrate to that highest energy, this is known as the transition state. That is a special term. That's your energy of activation. You definitely need to be aware of that. So now, one thing that I want you to be very careful with. There is a very definitive line when we talk about thermodynamics, and it's how thermodynamics and kinetics are not the same thing. I'm going to say that again. There is a hard division between thermodynamics and the kinetics of a reaction. So the thermodynamics of a reaction, that's stuff like in the Gibbs free kind of energy equation, right? So like enthalpy change, entropy change, spontaneity, right? All that kind of stuff. What about kinetics? Like, what is kinetics referring to? Because this is different. We don't cover chemical kinetics today. We're just doing thermodynamics. So we want to kind of draw that line. Yeah, rate, speed, energy of activation. And so you got it. We'll get into this in a second, Emily. But so when you talk about enzymes, enzymes are an example of a catalyst. They'll speed up a reaction via lowering the energy of activation. Here's a good example of one. But now the whole idea is, even though they're going to speed up the reaction, notice that they do not change the delta G. So if you have a catalyst, an enzyme is a great example of a biological catalyst, you're going to speed up a reaction, right? You'll get to wherever you're going faster, but you're not going to go any further to the right or further to the left. That's part of thermodynamics. And so exactly as Emily brought up enzymes, that is great for kinetics. We're not going to talk about it today, so we're going to kind of start off, as you can see, discussing what enzymes and, of course, any other kind of substrate would actually do here. Or sorry, catalyst. Sorry, catalyst would do there. Brain fart for a second. All right, so now one thing is, generally when we see a catalyzed reaction, as you can see, this is a catalyzed reaction, we generally approximate it and just like call it like this. But in reality, there's actually a bunch of different transition states. Notice that as you actually look at this process here, there's actually 3 specific different transition states. And so let's make this a little bit smaller so it won't take up too much space. There we go. Notice there's a transition state right there, there's another transition state right there, and there's another transition state right there. So why don't you all let me know, what are you, so actually, before we do this, so notice if you have 3 different transition states, you have, of course, your initial reactants, your final products, but you actually have 2 different whats. What would you call this, that little dip below your transition states? Special name that's different. It's your intermediates, exactly. And these are examples of a complex intermediate, as Christopher's saying. Like, you know, we have a complex of multiple things, but it's an intermediate. You guys are spot on with that. So then, what's your first intermediate? If you have an enzyme, you've got a substrate. Remember, the enzyme's going to catalyze the reaction, speed it up, but not change your free energy. You got it. So it's the enzyme substrate complex first. Then notice that the highest energy of activation there is going to be actually converting the substrate into the product. So notice that highest transition state, that highest energy, that's the hardest part of the entire thing. That's why it's got the highest bump there. So remember, this is your Gibbs free energy, so we're basically talking up top. This would be a very high energy transition state. Notice all these transition states are much lower energy now. Thus, would that make them more stable or less stable if they're lower energy? So these transition states, they're lower energy, thus they're more stable, exactly. So this would be very unstable up top there. These guys right here would be considered stable, which is how we get the thing to happen faster. Nice work. All right, so that's kind of like the gist of the idea of kinetics versus thermodynamics. If you have any questions on that, please put in the Q&A. That concept is crazy essential for the MCAT, like to really kind of have the difference between those two. And so now when we're talking about state functions here, this is referring to things that don't matter what the pathway is. We call these pathway independent. So all that matters is the initial and the final states. So examples would be things such as, you know, pressure, but in the thermodynamic sides of things, normally we'll see things like temperature, like delta H, that's your enthalpy, your free energy, your internal energy is U, S is entropy. We'll go through all these terms today. But so these are all state functions. So once again, these are path independent. That's what you need to write down for that. On the other side of things, we have process functions. So process functions are otherwise known as flow functions. It's either called process or flow. It means the same thing. The 2 classic examples are these. What are those 2? Q and W. What are those representing? Work and heat. Perfect, exactly. What are the units of both of these? Work and heat. They do have the same units. Joules, all right. So we're talking energy, right? But now this is very different because also if you look at the internal energy, that's your U right there, that also has joules. That's another type of energy. The difference is when you talk about heat and work, we're talking about energy moving between systems, right? So it's the transfer of energy, hence process or flow functions, because the thing's coming and going. Internal energy is different. That's the energy of that system, which could be changed by, of course, adding heat, which is a process function, but it's different. And we'll kind of show the difference between those two. Be aware, these are not state functions. They do depend on the pathway. So a good example would be right here. In fact, this shows you work. Since we know that work is the area under the curve, how could we solve what the formula for work is? We kind of retroactively do this, go backwards. So what is that formula for work then? It is P delta V. Nice work. We'll talk about the negative sign soon, Stephen. We'll get really into that today. But you got it. So just in general, to get the formula here, we'll just say P delta V. But I do agree with you. We'll talk about on and by and how positive and negative makes a big difference. We will get to that a lot today. But you got it. So work equals P delta V. So now the main idea is that means the area under that curve is showing the work. So now looking at two different processes here. So this first process, as you can see, what would that be? Would that be expansion? Would that be compression? What is that? That is, we've got some kind of, looks like we have a totally mixed bag here. Notice that it's going down and to the right. See, I'm kind of drawing the arrows as we go down this way. It is expansion, because notice what's happening. Your volume is increasing, and if volume is increasing while your pressure is decreasing, that means this system is expanding out, right? Volume increases means expansion. Volume decreasing means compression. So be careful about how you read these. The direction of the arrow on that slide makes a very, very big difference. And so you can see the little arrow there, and I drew in a couple others to make it a little bit easier to see where it's going. All right, so now that requires a certain amount of work. But now notice if you took a different pathway. We went straight across to the right and then straight down. Why don't you tell me what this first process would be here? Huh. So it's still going straight to the right. So it's still expansion, but specifically as Mary's bringing up, there we go, Tristan saying the same thing, it's isobaric expansion because you're increasing your volume, you're going to the right, but you're not changing your pressure. Exactly true. And then after that, we drop down, which is neither expansion nor compression because volume doesn't change. And what do you call it? There we go. That's one name is isovolumetric. What's the other name for that? When you do a process without changing the volume, nice, isochoric. So isochoric and isovolumetric, those mean the same thing. Perfect. So we're going through isobaric, then isochoric process. This is going to take a lot more work, as you can see. Much more difficult, much more of a pain in the butt, you could say, to go through that process. So the take home from this page is the difference between state functions and process functions. If you ever have work or heat, that does depend on the pathway. It's pathway dependent, you can say, whereas the other one is pathway independent. All right, so let's get our definitions out. We'll kind of get the big picture, and then we'll get some real specifics going here. The first is, notice heat, once again, it's joules. We talked about it before, but this is a flow function, so it's the transfer of energy into and out of a system. So we generally refer to heat as Q. What would be if you had Q was greater than 0? So what would that tell you about the process that we have? There's a special name we want to use this. Well, what's the name for that? Heat's going into the system, exactly true, Mary. So what do you call that? There's a special name for that even. Not gonic, that gives free energy specifically, Tristan. Right idea, though. Endothermic, exactly. So when you talk about heat going into a system, we call that an endothermic process. Now, notice when we say thermic, that does not mean temperature, right? It's because we're talking about thermodynamics. It doesn't mean enter temperature, right? Temperature and heat are very, very different. So do be careful with that word. It does not mean temperature. It means thermodynamics in general. So if your Q is positive, that means that it's an endothermic process, right? And then, of course, you could also say if Q is negative, that would be, we'll just get all of our terms down right here. As you can see, it's a definition page. That'd be your exothermic process, exactly true. So that's endothermic versus exothermic, just to get the big terms down first. And remember, these are flow functions. So on the other hand, temperature, this is a state function. So you can't have temperature enter or leave a system. That does not work. The temperature is describing a property of that system, and be aware that you have a direct link between temperature and internal energy. So like if you think about it, the hotter a room is, that means the more energy all the air in that room has. So then what does that look like? Like, let's get on a microscopic level. Like, so if you've got air molecules that are hot, how are they different than air molecules that are cold? What are they doing differently? Yeah, wiggling around super fast, moving quickly, because a lot of that energy is what kind of energy? It's also vibrational, wiggling, bond rotation, but the big part we talk about the most is kinetic energy. Exactly. You've got things moving. If you have things moving, you have kinetic energy. There's also a lot of potential energy in the rotation and twisting and torquing of bonds and the repulsive forces between gas particles. So internal energy is all of that stuff lumped together into one big category. We just generally talk about kinetic the most on the MCAT. So we often do kind of approximate this to our kinetic energy because they are directly proportional. It's just that there's lots of other things going on, such as the wiggling and all that other stuff that you guys said too, and repulsion and whatnot. Perfect. So do be aware of this. Temperature and internal energy are not the same thing. They are directly proportional, right? So energy is joules, right? Heat is joules. Temperature doesn't have joules. And you can't say something equals something if they have different units. So that's why we have to say that temperature and internal energy are directly proportional, but they're not the same because they do have very different units. That's also why, what do we know about when Kelvin drops all the way to 0? So like, what's the deal with that? And this is why, temperature and internal energy are directly related. You got it. So we call that absolute zero, and so there is no movement whatsoever, no entropy, no nothing. The molecules themselves are completely stationary and aren't moving. And so if they're completely stationary, that means that there is zero internal energy. Exactly true. So that's why we have that relationship. And, we haven't actually gotten to absolute zero yet, but I actually live in Colorado, and we got at the University of Colorado in Boulder, for the physics department I used to teach for them, they got down to, I think it was 0.0001 about Kelvin. So really, really, really freaking close to absolute zero, and things get super weird when you get that low. It forms a whole new phase of matter called, they named it a Bose-Einstein condensate. It's just freaky, and like you start to see the wave functions that you can't normally see in matter, and it gets really complicated and way outside the scope of the MCAT. But you do need to know what absolute zero means, and it means there is no internal energy, thus no movement. So that's the key. But yeah, if you want to look up some Bose-Einstein condensates, oh my god, that's some really neat research has come out recently, so it's pretty neat. I don't know. I don't think it's possible to be colder than absolute zero because, things are already frozen. But I get where you're getting at. I hear there's lots of snow out there. All right, so that's the big thing here. So then when we talk about work, heat, and internal energy, there's a very important equation for you all to know. What is the equation that relates work, heat, and internal energy all together? This is your master equation for thermodynamics. Nice. We'll get to that soon. That's more for changing temperature, right? But you got it. It's U equals Q minus W. And there is your formula right there. Now, one thing I do want you to know, because the MCAT tends to be pretty standardized in terms of the way that they test this, and so we definitely want you to be aware that when you see this formula, remember that it is work done by the system. And as I said, I would get into this more today, but we will really kind of dive into it. But keep that in mind. This is defining the work done by that system. So let's, before we get into this right here, let's just real quickly talk about this. We're going to come back to it again, but I want you guys to visualize what that means when I say, work by a system and like what that's even really referring to. So let's say that we have a system. We'll say that we have this blue box right here, and this blue box is some kind of gaseous system, right? So you've got all these little particles. They're bouncing around inside the box and bouncing off the walls of this container. So now, with that in mind, let's think about the different types of, once again, what's the formula for work? What's the formula for work once again? Yeah, and Sergey's got the actual relationship for you too. That's a good point. So he's got the legit full relationship between these two. Yeah, we say work's equal to your pressure times your change in volume. So now notice when we talk about this, we're talking about pressure, right? And so pressure is the force that's being applied to the walls of the container by the gas itself. So this is also some of your physics concepts that relate force and distance and pressure and volume and how it's all actually the same formula. But so the thing is, if you look at these purple arrows, it's the pressure or the work of the particles bouncing against the walls. Would these forces here, would they be work doing on the system or work done by the system? Christopher says by. And we do have most people saying by. You got it. These purple arrows would be defined as the work done by the system, because if this system is a bunch of gas particles and they're bouncing off the walls of the container and trying to push out, that means that the system's doing work. It's trying to push out, it's trying to expand. Thus, work by the system would equal as expansion. And you have to define the system, Christopher. They must define what the system is in every single problem because it's different every single time. So exactly. So in this case, the box itself is the system. The gas particles inside that box, of course, is the system itself. Cool. It is. The case itself is the system. So this box is the system. And the thing is, every single time they will define what the system is itself. So notice if there's work being done by the system, that would mean the system is expanding against its surroundings because it's pushing out against surrounding. It's getting bigger, 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 bigger. Conversely, we can look at the other side of the token. If we look at the other side of the token, let's get a different color to make sure this is consistent. If you have, of course, the air pressure of the outside normal world is pushing on this balloon or box or whatever it might be, that would be referred to as work done on the system. And that would mean compression. So this is always going to be true. If you ever are talking about work being done on the system, that means that you are compressing that system. Conversely, if you're ever referring to work done by a system, you refer to that, of course, as expansion. That system's expanding out against its surroundings. Now, here's where things get a little bit weird, and I like how Christopher brought this up. But so the thing is, generally speaking, what do we define things as? What do we define things as? Is it work on or work by? What's the standard for the MCAT? How do we always really refer to things? The standard is by. Like, that's just in thermodynamics. The way that we define work is we define work as the work done by that system. So then, if you have compression, if you're doing work on the system, what would that mean about work done by that system? It means it would be negative. So notice you could say then work on a system that's compression. So then if you have work being done on a system, you would have to say work done by that system is negative. So here, actually, let's do one more. I want to do one more thing, and I'll get out of here. But this is, I think, one of the most confusing things for most folks, so I really wanted to spend time with it. Cool, good to hear. I like it. I love seeing light bulbs. It's perfect. So what's the other formula for work? Let's tie this back to your intro physics stuff from way back in the day. What does work mean? Once again, force times, wait, what's D mean? Once again, force times. It's not distance. Be careful. Everyone says that. It's displacement, Connor. Exactly. So be careful. It's got to be displacement. I know everyone says distance, but it can't technically be distance. It has to be displacement. It's, basically talking vectors versus scalars is the difference here. But so here's the reason why I want to get into this, and I'll show you why this makes a difference. So if we want to talk about the work done by the surroundings, right? So let's look at this right here. So notice this would be considered work done on the system, as we said. So now if we take this system, and if we were to grab this system and we were to actually compress it, what would your displacement vector be? What would the direction of your displacement vector be? Your displacement would be defined as down, because we just squished this box downwards, right? So now notice, if your work on the system is pointing in the same direction as displacement, then what would work on the system be? Positive or negative? Since they're pointing in the same direction, work done on the system is pointing downwards, displacement is pointing downwards. If two vectors point in the same direction, it's going to stay positive, right? On the other hand, if we say that we're squishing this box like we just said, and we're like, all right, we're squishing the box, the displacement is down, but the question stem is defining it as what is the work done by the system, thus these purple arrows pointing up. Well, if displacement is down and work by the system is pointing up, then what's going to be true of the sign of work done by that system? It'd be negative, right? So, of course, force times displacement, they're both vectors. So if one's positive and one's negative, if they're pointing in opposite directions, your net is going to have to be negative. That's why you could say expanding, right? You could say work done by the system is positive. So you could say work done by the system is equal to a positive when you're expanding. Conversely, if you want to talk about expanding and work done on the system, then it would be negative. The whole idea is it's just vectors. And so if the vectors point in opposite directions, that means that they will always have a negative sign. Conversely, when you're talking about compression, same thing. As we said, if you're ever defining this as work done on the system, then work done on the system is going to be positive every single time. And if you wanted to define it somehow as work done by the system, then of course it would be negative. So on the MCAT, if they are going to test this, if they're going to not stick with the standard by the system, they will tell you what is the work on the system or what is the work by the system. But the thing to keep in mind, if they don't define it as on or by, we must assume by because that's the standard. Cool, exactly. So yeah, Christopher, just think of the vectors, right? So of course, notice like by always means expand, on always means compress. So if you're ever compressing a system but defining it as work by, well, work by would mean outwards. Compress means inwards. Opposite signs means it's negative. So that's the main thing you need to do is compare your signs. If they're ever pointing in opposite directions, it will be negative. If they're pointing in the same direction, it'll always be positive. Just remember that work on means, like if you have, I wish I had like a bouncy ball or something. But if you would compress something, that would of course be work on the system, right? Whereas if it's pushing against you, that means it's doing work on its surroundings, thus work by the system. Like a balloon crystal, exactly, you got it. All right. Remember, these are all recorded. If you guys are brand new to thermodynamics and you're like, oh my gosh, this just went way over my head, go through the chapters in your Chem Phys books, then come back, watch this again, see if it clicks. Sometimes it takes a couple times because this is some complicated stuff that we're talking about. And to be totally honest, this whole work on, work by system stuff tends to be the most confusing for most folks. It really is. And so I wanted to kind of cover that now, get it out of the way. We're going to come back at the end and go through some practice problems on that. But since that tends to be the most confusing part for folks, I wanted to spend extra time on it. All right. Perfect. Perfect. Thanks. Glad to hear it, Emily. Thank you. I like thermodynamics. I'm a little bit of a nerd, if you haven't noticed. All right. So let's change gears though. So we'll come back to the on the stuff, the by stuff. Let's talk about the phase change, the heat transfer, and all that kind of stuff. Perfect. Awesome. All right. So let's talk about heat capacity first. So the first one is heat capacity is energy needed to raise temperature of a sample by 1 degree. We generally don't see this as heat capacity. We generally see this as specific heat. Notice that this is the exact same formula. So notice heat capacity is just equal to the mass times the specific heat. In both of these, those little c's is the specific heat. So what determines the specific heat? So this, I know it's the same formula. It is the same formula. But be aware, heat capacity means you're multiplying by mass. Specific heat, you don't need to multiply by mass. It's just the characteristic of the substance itself. As Molly's saying, Tristan's saying the same thing. It's like, exactly, it's intrinsic. It's a property of the element, right? So for example, do you guys know something that actually has a very low specific heat? Thus, it's a very good conductor of temperature. There's a couple types of metals that are really good at transferring heat. Copper, silver, gold are actually our three best ones, the very expensive metals. But you got, well, at least when it comes to just, metals themselves in their atomic state. Not cool things that we can make as humans, because we've got some other cool things we can make. But exactly, it's a property of the metal itself. Copper is a classic example. It has very low, it has very high thermal and electrical conductivity, which means heat transfers through it very easily, as well as electricity transfers through it very easily, which is why we use it for, of course, heating pipes. Water pipes, generally all the hot pipes are made of copper, as well as, of course, all of your, the wiring in the house tends to be copper too. Cool. All right, so that's kind of like the general idea here. You might notice this formula then. What would that formula be used for? What's that formula used for? Bingo! Is it Pear-Stew? That's exactly right. You got it. Totally correct. Not quite phase change yet, but we're talking about changing temperature. Let me know if I pronounced that incorrectly too. Perfect. You got it. So this would be, notice, changing the temperature. You might also notice that this formula, perfect, Q equals MC delta T. Wow, that looks so familiar. I feel like I've seen that word before somewhere. Yeah, it's MCAT, because notice when you're taking the MCAT, you're feeling the heat, right? Stressful times. At least it can be stressful times. I know, that just happened. We just got cheesy. All right, so it's a way to remember the formula. That's the main thing. As long as you remember it, that's all that matters. And so let's talk about this for a second. So as we said, I want to real quickly recap. Remember, specific heat, it's the energy required to increase the temperature of that compound. So I'll let you guys do this first, and then we'll kind of retroactively go back and talk about why. But what's going to burn your mouth? The cheese or the crust? The cheese. We've all done this before. You get the cheese stuck on the roof of your mouth. It burns it. So then what does that tell you about the specific heat of cheese versus crust? Which one has a higher specific heat? The cheese has a higher specific heat. So now, here's the reason why. If we had something like copper or something like that, as soon as you took it out of the oven, since it's such a good conductor of heat, it would give its heat to the environment very quickly. Cheese, on the other hand, is really crappy at giving away its heat because it's a very, very high specific heat. Thus, it's really good at basically maintaining its heat once it gets hot, or you could think of it that it takes a very long time to heat it up. Like, for example, have you ever put a pizza in the oven, and then by the time the bottom of the thing is burnt to crap, the cheese in the center still hasn't fully melted yet? Has anyone noticed that before? There we go. Exactly. So the thing is, it's because the cheese is very high in water content, and the higher the water content, the higher the specific heat. The higher the specific heat, what that means, it takes more energy to heat it up, and then once it's hot, it takes a long time for it to give its heat away. Water's classic. It's really, really high specific heat. It's one of the highest that we normally see. Exactly. You got it, Crystal. So there's a way we can actually use this to survive in the woods if you're camping. So let's say that you found yourself on a camping trip. Temperature drops. It gets really freaking cold out. You're worried you're going to freeze to death because your sleeping bag's no good. All you need to do, remembering the property of common materials like water, put some water on your camping stove, heat it to a boil, dump it in your like Nalgene type bottle, seal it up tight, then throw it in the bottom of your sleeping bag. Since water has a very high specific heat, once that thing's hot, it's going to take hours for it to dissipate that heat. Thus, it will slowly release heat in your sleeping bag throughout the entire night. Whereas if you did this with like a piece of metal or a rock, what's going to happen is it's going to get super hot, it's going to get rid of the heat really quickly, and it's going to melt a hole in your sleeping bag. Water can't get hotter than 100 degrees Celsius, right? So it can't get hot enough to actually melt your sleeping bag. And as Tristan knows, it totally works. It totally works. So keep that in mind. Same reason why if you put an empty pan on the stove, the empty pan gets crazy hot, crazy fast. You fill that pan with water, and it takes forever for the water to get warm. And it's seriously, Tristan's right. It works freakishly well. You notice a lot of those like actually like heaters too, they actually are like bags. You like basically heat up water, put into a bag, and then it keeps you warm throughout the night. They're pretty useful. Cool. All right, so that's specific heat in general. Higher the specific heat, the more energy it takes to heat it up, thus also the longer it takes for it to give its heat away. All right, so now latent heat is talking about what? Wait, heat absorbed that does not change the temperature? What would it be dealing with? Totally true, totally true. You got it, phase change, right? So it's the heat that enters a system that doesn't change the temperature. Thus, wait, so you would call phase change a what type of process then, to get back to our terms that we had before? Phase change is a type of a, well, that's a type of, you got it, isothermal, yeah. So isothermal means that the temperature doesn't change. So phase change is an example of an isothermal process, and as Mary's got in the chat right there, this is our formula for phase change. It's actually much easier. Notice all you do is you take the L, that's the latent heat. It's a constant. We don't memorize it, and you multiply that by the mass. So all the little m's here are just masses. You got it. So now you do not need to memorize any of the latent heat values for any kind of material. The only thing you really need to know is the specific heat of water. So that's the little c right there. Sorry, I just got the hiccups all of a sudden. What is the specific heat of water? So give me units though, because it totally depends on the units. There we go. Tadel, exactly true. So it's 1 calorie. That's per gram Kelvin, which would be the same thing as 1 milliliter Kelvin. That's a neat thing to know about water. 1 milliliter of water is 1 gram of water is 1 cubic centimeter of water. Those are all the same units, whether it's a cubic centimeter, milliliter, or gram. It's all the same. And then the other one is 4.184. What's that referring to? It's not calories. It's 1 calorie. 4.184 refers to joules. Nice work, everybody. So it's either 1 calorie per gram Kelvin or 4.184 joules per gram Kelvin. Or you could say per milliliter Kelvin, or you could say per, centimeter cubed Celsius, because your difference in Kelvin and Celsius is the same. The absolute values are different, but the changes are the same. So you can say Kelvin or Celsius, you can say gram, centimeter cube, or milliliter there. It's all the same thing. Doesn't make a difference. Cool. Perfect. You don't need to worry about that, Emily. Not necessarily. Yeah, I wouldn't relate the two because it really depends whether you're talking about metals versus non-metals. And so I'd be wary of drawing the lines between, to be totally honest. Because, man, talk about phase changes of metals versus phase change of water. You're talking scales of difference. You know what I mean? So just totally different categories. But, I mean, we could maybe find some trends, but I would be wary of drawing any hard lines. Just because, it really matters on the material. It's very dependent on it. It's a very good point, though. All right, so that's, of course, the delta H of the phase change, which, once again, you don't need to memorize any of these for the MCAT. The only thing you need to memorize on the page is what these numbers are referring to, and, of course, these numbers for water. You got to know a lot about water. Super common. All right, so I'm basically just going to show, so these are the equations we learned here. I'm just going to show you how you would apply this in context. So notice, if you start off with negative 30 degrees ice, what's the first thing that you're going to have to do? If you have a negative 30-degree block of ice, and ice can get colder than 0, for sure. Before you melt it, you got to do one thing first. There we go. It's exactly true. You need to first increase the temperature to 0 degrees. Then it can start to melt. And when it starts to melt, what happens to the temperature? So first heat it up to about 0 degrees Celsius. Then it stays flat, and it does not change the temperature as you're actually melting it. So once again, we said melting or boiling or any kind of phase changes in isothermal, temperature does not change during that phase change. So then once all that ice is melted, then you start to heat it up. Notice here's the formulas that you would use. Of course, you get up to 100 degrees Celsius, and then once you get to 100 degrees Celsius, then you boil it. So then, of course, the next phase would be boiling. And then after that, you have to heat it up all the way. If you want to heat water to higher than 100 degrees Celsius, you first turn it into steam, and then the steam you can heat up to higher than 100 degrees Celsius. That's why I don't know if you guys have ever been working in the hospital or out in the field and seen people with steam burns. Have you ever come across steam burns, either in life or in practice when you're doing medicine stuff? They're kind of horrifying. Like, yeah, they're like pretty much the worst burns you can get. They're well, not the worst, but they're pretty far up there. Because notice that if it's a steam burn, by definition, it has to be hotter, or most likely it will be hotter than 100 degrees Celsius. So you're talking really, 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 really hot stuff. Um, oh, nasty, nasty, yeah. So yeah, there's been horrible things, but yeah, I won't get into it. But do be aware, stay away from steam burns. That's why you want to be careful whenever you're exposing yourself to steam, to be very careful. I know a lot of people actually burn their faces pouring boiling pasta into a colander because the steam bursts up and hits them in the face. In that case, it would only be 100 degrees Celsius, but that's still really freaking hot to expose your face to. So yeah, be careful pouring out pasta. Don't burn your face off. Life lessons in today's class. All right, so yeah, just stay away from pasta in general. You don't have to worry about it. All right, so here's just the application of all of these different equations we did on the previous page. All you would do then to get the total energy added across this entire x-axis is you would add all of these values up. So what I want to do is, instead of just doing math, because we can do math later, let's just talk about the trends and the shapes and all that kind of stuff here. So why in the world do you think that if you look at this line here, why is that line for vaporization so much bigger than the one for fusion? Why? You guys are totally right. It takes a lot more energy. Why does it take so much more energy to turn liquid water into steam than to turn ice into liquid water? Tell me more. I mean, you're right. It is super crazy, but Tadal's getting to the point there. So notice that when you turn ice into water, water can still hydrogen bond, which means it still has a lot of intermolecular forces. Once you turn water into steam, you have to break every single intermolecular force. Not only do you have to let it break all those intermolecular forces and turn into gas, but then additionally, gas has a lot more kinetic energy as well, Tristan. Totally true. But you got it. It's a hydrogen bonding thing. It's an intermolecular forces thing. It's primarily, but of course it's also, kinetic energy in that. But the reason water's got a really, really high heat of fusion is because it really does have a lot of hydrogen bonding in the liquid phase. You got to break all those intermolecular forces. So it's significant. It takes a lot of energy to boil water, as you know. All right, next one we have for you is, what would the curve change if the ambient pressure was dropped down to 0.95 atm? So if you drop the atmospheric pressure, how would this whole thing change? Yeah, exactly. You got it. Always takes more energy to evaporate it than melt it. That is always true. For water, at least. Probably most things, actually. Probably almost everything would. What goes down? One specific thing's going to decrease. Tell me what's going to decrease. Nice, Leanne, exactly. You guys got it. The boiling point, the temperature of that boiling point. If you wanted to boil water at lower altitude or higher altitude, thus lower ambient pressure, this drawing would basically drop. It would start sooner. It would boil at, instead of 100 degrees Celsius, it would boil at around, maybe 98 degrees Celsius. It doesn't change for melting, because the reason is, what's the definition of boiling point? What is, and let's get this, because this is huge. The MCAT loves it as boiling point. So boiling point equals when bingo, you guys got it. It's when the atmospheric pressure is equal to the vapor pressure. So the vapor pressure is the vapor you're forming of the liquid turning into a vapor. And as soon as that meets and exceeds the atmospheric pressure, it just starts to turn into gas and basically breaks away from the atmosphere. So the higher the atmospheric pressure is, the higher the boiling point is going to be of water. And that's how autoclaves work. And actually, Kyle and I were chatting about this before in class. Autoclaves, you guys have used autoclaves in lab before, I'm guessing, correct? Probably at some point. It's just like a metal box you put in your tools in and expose it to crazy high heat and crazy high pressure. Because if you can pressurize water, the water will get way above 100 degrees Celsius before it boils if you increase the pressure in that system. By decreasing the pressure of the system, like here in Colorado, water actually boils more easily. So it only boils at like 98 degrees Celsius. I'm actually in Keystone right now. It's probably about 97 degrees Celsius here. So which screws up baking, which is why you sometimes see high altitude cooking directions, because the higher the altitude, the more easily water boils, thus it boils at lower temperatures, so you have to adjust your recipes because all the temperatures are basically different. Hence high altitude cooking directions. What about this? What if you were extreme, you went to Mars, where the ambient pressure is only about 0.001 atm, then what's going to change? There's a special word we want. It's a very, very low boiling point. What's going to happen? There we go. Tadell's got it. What's that called? You're going to directly turn a solid into a gas. Sublimation, Keely. Nice work. You would sublime. Because the thing is, you don't even have a liquid phase if there is no ambient pressure, because the vapor pressure equaling atmospheric pressure causes things to boil. If there is no atmospheric pressure, things just naturally boil. There's nothing keeping them down. That's why if you look at Mars, for example, there is no longer any atmosphere, but even though there's no atmosphere in there anymore, there's still liquid ice on the cores. Because as soon as that heats up, it doesn't turn to liquid water, it evaporates right away, and then of course leaves and goes into space. Poor story, Mars lost its atmosphere, so it can't have liquid water anymore, but it did have liquid water in its past. Back in the day when it had an actual atmosphere, but yeah, it lost its magnetic field, and now it lost everything. Poor thing. You got it. As Hannah says, space. All right, so we're gonna switch towards questions now. So let's throw your answers into this poll first and foremost. After that, we're going to start doing some more isochoric, isobaric, adiabatic type stuff. Cool. I like it. We are actually, I'm just going to answer this because we're getting mostly correct here. It's B. You guys are totally correct. It is B, because here's the thing. Whether you are vigorously boiling the water or if you are barely boiling the water, what's the hottest water can get? Whether it's vigorously boiling or barely boiling, its temperature is going to be 100 degrees Celsius. So any extra heat you put into that system is going to go into turning your water into vapor, which means it's leaving the pasta and not even cooking the pasta anymore. So the only time you'd actually want to vigorously boil is if you're trying to boil off the water, which is important in making reductions and a couple other recipes. But if you're cooking pasta, you're not boiling off the water. You're going to dump it out anyways, right? And so you might as well just barely boil it, because it's still going to bring it to the exact same temperature. So they both cook at the same time, 100 degrees Celsius no matter what. All right. So before we get into all the other kind of stuff, we got to talk about the transfer. So we mentioned this previously, but we haven't gotten too deep yet. So what is conduction? We'll go through the three main types of energy transfer, and then we'll do some processes. So transfer of heat due to what, though? Contact. Nice work. It is collisions. Of course, we're talking on a very atomic level, but kinetic energy between your microscopic particles. So, for example, if this particle is very, very fast, it's moving quick. I mean, if it's hot, it's moving quickly. This one's slow. It means it's moving more slowly. When they touch, they basically equalize. So whatever has higher energy gives its energy to the thing that has lower energy. Thus, whatever is hot gives its heat away to the thing that is cold. This is very important. So there is no such thing as transferring cold. You can only transfer heat. So of course, like when you touch something cold, the reason that it feels cold is because it's sucking the heat out of your hand when you touch it. So there is no such thing as transferring cold, just heat. Direct contact, that's conduction. You got it. All right, so this is determined by thermoconductivity, which of course is shown in this formula right here. You don't need to memorize this formula. So let's think about this first of all. If you have high thermal conductivity, would conduction happen more quickly or more slowly? If you have high thermal conductivity. Talked about this before. Super quickly, exactly. So once again, we said like silver, for example, has very high thermal conductivity. So if you want to do a little experiment, this is kind of fun. If you do have, like, let's say you go back to the parents' house and they have like the fancy silver set, you know, like the actual legit pure silver things, which you only bring out for special occasions, but once in a while we pull it out. If you were to stir coffee with a legit silver spoon versus stirring coffee with an old school spoon, I mean a normal spoon you buy for cheap at the thrift store, what would you notice about stirring it with the silver spoon? Mary's got it. It's going to heat up way faster, so it's going to transfer the heat into your hand a lot sooner than the cheap spoon that you get that I don't even know what it would be made of. But since actually silver has the highest thermal conductivity, so I know silver would be faster than whatever metal the normal cheap spoons are made out of. You got it. Perfect, exactly. Only transfer heat. We do not transfer cold. Nice. All right, so this formula here is just the formula showing it. You don't need to memorize this for the MCAT. Really what it's showing you, this here is power. So power is watts. Watts is energy per time. So of course it's going to, how long it takes basically, or the rate at which energy is going to be transferred. K right there is your thermal conductivity. And then it's just other things like length, we would assume. Cross-sectional area also makes sense. And then the difference in temperature too. So that's the only difference right there. So don't memorize the formula. Be aware of it. The higher the thermal conductivity, the higher rate that you can transfer energy. As we said, Metals are very, very conductive for heat and electricity. Non-metals are pretty crap at it, though. All right, so now last two are convection and conduction. What's the deal with convection? Convection has a keyword. There's a very key word to convection. Not necessarily water. Flows, you got it. Flows getting to our idea. Fluid. Remember, fluid does not mean liquid. Fluid is both gases and liquids. Be very careful with that. So it's the bulk movement of fluids. It's very fast transfer of heat. You got it, Christopher. The idea is and how convection works. Like, for example, a convection oven. What does a convection oven do differently than a normal oven? How does it cook food way faster, which is totally true, as Christopher is getting at there. It's much quicker cooking. It just, all you do is you put a fan in the back of it. If you put a fan in the back of it and it blows hot air over the food, it actually it heats it up much more quickly. Or conversely, I'll give a different example. If you ever jumped into an ice cold stream, jumping into an ice cold stream is a lot colder than jumping into an ice cold lake. Because when you jump into an ice cold stream, all that cold water hits you, steals your heat, and then goes down the stream where brand new cold water can hit you. And that's what wetsuits do. Wetsuits don't stop conduction. You're wearing a wetsuit, you're still getting wet, as the name implies. What it does is it stops convection. As your body heats up the water molecules inside of your wetsuit, it keeps that hot water molecules next to your skin and prevents convection from pulling it away from you and getting you cold. The air, that's called the dry suit, Hannah. That's actually different. Dry suits do keep you dry. Wetsuits, you're still wet. It's just that it keeps the water around you warm, basically. So same idea, but there are dry suits, too, that actually keep air in there. But they're slightly different. So yeah, it's okay to pee in a wetsuit. It's not okay to pee in a dry suit. That's a good thing to be aware of. All right. So, because, you know, the wetsuit's full of water anyways. No big deal, right? It's just going to heat it up faster. It's an old surfer trick. Exactly, old surfer trick. All right. Yeah, there we go. Hannah's probably got the better idea there. Better idea. All right, so the next one's radiation. Radiation is transfer of energy. It doesn't have to be through a vacuum, but it's electromagnetic rays. So let's say, for example, that you, I don't know, like you stick a metal rod in a fire for just like a minute. You take it out. It's not like glowing hot or anything. What kind of electromagnetic radiation is a hot metal stick going to be emanating? Not like red hot, just it's like a little bit hot. It's like maybe a couple hundred degrees, if that. What kind of radiation would be emitted by a hot object? Whether it's metal or you. You could leave a t-shirt in the sun. Leaving a t-shirt in the sun will also emit a certain type of electromagnetic radiation. Not alpha particles, those are actually helium ions. That'd be pretty huge. What type of electromagnetic radiation? Remember, it's a hot t-shirt. Thus, it's going to be emitting infrared, Keela. Exactly true. So infrared, that's low energy electromagnetic radiation. It's basically emanating heat. That's infrared. As it gets hotter and hotter and hotter and hotter, though, what's it going to start to emit as it gets really freaking hot? So you move up the energy spectrum from infrared into finally visible and then UV and then eventually like crazy hot stuff. But that's why when something starts to get hot, eventually it starts to glow. Because once it's glowing, it's actually emitting visible electromagnetic rays, whereas before it's actually that hot, it's still emitting infrared. And that's how those infrared cameras work. You can see a bunch of heat signatures and stuff with those. Very popular in the military these days. All right, so that's radiation. It's electromagnetic rays. If you don't know the electromagnetic spectrum from radio waves all the way to gamma rays, study it up. You got to know that stuff. That's definitely high yield. So do be aware of that. Especially with the new way the MCAT's being tested. It's going to tie in a bunch of stuff that would relate to physiology with, you know, X-rays and cancer and various things like that. So solar radiation is a good example. Travels through a vacuum perfectly fine. So question we've got for you, where's it going to be colder? On a clear night or a cloudy night? So clear night or cloudy night? When would it be colder? Keeping all this stuff in mind. Tristan says clear night. Benjamin, you guys are right. It is a clear night. Because if you have a cloudy night, here's the idea. Throughout the day, the sun hits the earth. And as the sun hits the earth starts to absorb energy, heat up, and start to emit infrared heat. Starts to basically get hot. If it's a cloudy night, then as the earth is already hot and starts to dissipate that heat, the clouds trap the heat in, thus keeping it warmer. If it's a clear night, that heat leaves the earth, goes right back out to space, and is gone forever. This is where the whole greenhouse, you know, what do we call it? Global warming, greenhouse gases, or greenhouse effect, I think is the way we say it. But that's what it does. By having clouds, it traps the heat in that's already made it here from the sun. Exactly. It's like a fuzzy blanket with a bunch of rainbows and stuff in it. Exactly true, Amber. You got it. Like it. Super comfy. All right. So that's all the transfer and the different mechanisms you'll need to know for test day. All right, so the last thing we're going to talk about today, we've already went through this, so I did it previously. This is just going to cement in what we talked about. We already talked about work. We already talked about how expansion was work done by the system being greater than zero. Work done by the system, work would be less than zero. We covered this before. And so this is literally what we just did. This is the same thing we did previously. I just want to now apply what we covered before in the context of this chart. So this chart's going to be pretty much the last main thing we go through today. It's discussing the different types of thermodynamic processes. In our next therm class, which is going to start in 10 minutes, we're going to really get into the application of these. So this is huge, but we will elaborate much more on these in the next class. I just want to let you guys know that right off the bat. All right, so here are the things we need to know. When you see something is adiabatic, what does that mean? Christopher's got the keyword. If it ever says quickly or rapidly, it's an adiabatic process. I'm going to say that once again. If you see the keyword of rapid or quick, it's adiabatic. You gotta know that. All right, so now what's constant, as you're all saying, is there is no heat entering or leaving the system. Now, once again, heat is not the same as what? We love to confuse these, but it's different. Heat is not the same as temperature, exactly. Notice, isothermal would be no temperature change. Adiabatic means no heat change. That is very, very different. And what's that big formula that we'll use to relate all these things together? What's your big formula? The most important formula of them all? You got it. So your change in internal energy is equal to the heat minus the work done by the system. All right, so now that means, so now by definition, if we're either compressing or expanding, there is going to be some work done either on or by. We won't worry about that yet. But so now, notice if you know that Q is not changing, since you can eliminate Q from this equation, that means any compression or expansion is directly going to result in change in internal energy. Thus, what's going to change if you change the internal energy? What's directly proportional once again? To internal energy specifically? Temperature, exactly. So if there is work, and now we have a relationship between work and internal energy, I see what you guys were saying there, but that means if you change internal energy, you will change the temperature. So here's my question for you. If you rapidly compress something, we know we're going to change the temperature. Would you expect it to get hot or to get cold if you rapidly compress something down in a tiny little space? We're getting mixed. It is hot. You're going to increase the temperature. Because remember, internal energy and temperature are the same thing. If you take a bunch of gas and you compress it into a tiny little space, are those individual gas particles happy or pissed off about it? You cram a billion of them into a tiny little cube. They're bouncing off the walls. They're hitting each other. There's tons of repulsion. There's tons of energy, exactly. And if they're bouncing off each other and there's lots of interactions and energy, that means that it's a very high energy system. Thus, it's more high energy, exactly. Cool. Not necessarily the same crystal, but more energy in general. More collisions, more energy. Not necessarily velocity. We can get into that. Throw in the Q&A. We can get into that more specifically. But exactly, yeah, it's a lot of energy in a small space. Cool. So then, of course, if you rapidly expand, think if gas particles are expanded out really huge, they're all of a sudden like, whoo, I don't know where I am, no big deal. Everything cools down, everything gets really cold. Cool. All right, so now if you wanted to, of course, you could also use the formula here, right? Because we said it's negative work done by the system. We said work is equal to pressure times change in volume. And if you're going to compress, what does that mean changing with your volume? So true. I like the analogies. So notice if you're going to compress a system, that means that you have a negative change in volume. And if you have a negative change in volume, this term is negative. Negative times another negative gives you a positive. Thus, you get an increase. So notice you can do it mathematically or you can do it conceptually. I personally really prefer the conceptual way to solve it. I think it makes it easier. All right. So let's go on to the next one. So we said isothermal now, there is no change in temperature. So how could you then rework this formula we have up top to say there's no change in temperature? So what's not going to change for isothermal? You've got no internal energy change. So that means any work that is done is going to result in 1. So if exactly, you have a direct relationship between work and heat. Exactly. So then if you basically apply work to that system, you work that system, right? That means that if you're increasing the work, you're going to increase the heat that is leaving that system. So notice if you compress it, you're going to compress it. It would want to get hot. You're not letting it get hot, so the heat leaves the system because you can't change the temperature. Same thing for expansion. Isothermal means temperature doesn't change, so exactly the formula that we have in the quat there, saying it, the work is directly equal to the heat. You compress it, it lets heat out. You expand it, it sucks heat in. Exactly. Other way around. Yeah, we'll go through this in the next class. We're going to go through this in the next class. We're going to jump in a second. So the beginning of the next class, I'll discuss all this stuff again. Let's just knock out isobaric and isochoric, and the next class we will continue to discuss this stuff. Why don't you guys just tell me what these two mean? So what's isobaric mean? What's isobaric mean? No change in pressure, exactly. So then let's think of an example. If you take a balloon's a good example of an isobaric system, and you bring it outside, what happens to your balloon? If you bring a party balloon outside in the winter, it's winter right now, right? I think it's winter. In the winter, it's cold out, it shrivels up, it's compressing. Notice you have a relationship between compression. When it gets cold, it shrivels down, and then of course if you put it into the oven, it would swell up really big and get very inflated. You got it. So very last one, isochoric, we said that means no change in volume. So then, can you compress or expand if there's no change in volume? Can you compress or expand if there's no change in volume? No, you can't. So then all we can say then, if there is no work, notice you cross out the W in the equation. It's the same one as before, but any change in Q results in a change in delta U, thus temperature. All right, so what we're going to do, we are going to talk about this stuff a whole bunch more in the very next part of our next class, which is going to start in exactly 5 minutes. In the meantime, we're going to take a short break. We are going to keep running the Q&A in the meantime. But take a quick 5, give you a little survey. We'll come back. We'll talk about our last part of class, and we will reiterate these points because we have to if we're going to talk about engines. All right, I'll see you guys soon. I hope you had fun. I hope you learned a lot. Remember, if this went fast, you can always come back and watch the recordings again. See you soon.